Hello, and welcome to the second episode of SpaceTyme. Today I'm joined by Professor Alfonso Aragón-Salamanca, who is a head of the Nottingham Astronomy Group and currently specializes in extragalactic astronomy and observational cosmology. First of all, I'd like to extend my thanks for you agreeing to be on this episode. Why don't we start off by you introducing yourself to our audience, giving us a bit of a summary of your background and your current research.
Well, thanks for giving me this opportunity. I'm an astronomer. I was an undergraduate in Madrid, and then I did my PhD in Durham back in 1988. Then after that, I spent some time in Cambridge, and then I moved to Nottingham just over 25 years ago, where we started the Nottingham Astronomy Group. That started with really 5 of us, and now we've pretty much filled 3/4 of this building, so we're the best part of 40 people. That was very interesting for me because it was moving from a place like Cambridge, in which astronomy had been there for many years, many centuries, and here there had been no astronomy, no really much research in astronomy. So it was challenging to come here, starting something completely new. Getting the undergraduate courses going, getting the PhD program going, getting the funding for research. It was challenging and it was risky. Could have not worked, but it did in the end. And about maybe 12 years ago, I became the head of the astronomy group here, following Mike Merrifield, who was one of the people who funded the group and who moved here just slightly before me. I do research and teaching in astronomy and in physics, and my research is mostly on how galaxies form and evolve. I'm mostly an observer, so I like using telescopes and data from telescope to observe galaxies in many different environments and many different types of galaxies, trying to understand how they change with time, so how they evolve with time, but also how the environment, that is where they actually live, affects the galaxy's properties and their evolution. Galaxies that are isolated and galaxies that are in dense regions do not have the same properties. A little bit like human beings. A person that lives in the middle of Manhattan probably doesn't behave the same like a person that lives in the middle of the Sahara. There are different environmental effects that make them behave and develop differently, and the same a little bit with galaxies.
What was the sort of spark that inspired your focus in this topic in the first place?
Well, I always liked science, and when I was at school, I liked pretty much all sciences. I think I could have just as easily be a biologist or a geologist or a chemist or a mathematician. I like science, and what happened is that most of the time when I was in high school back in Spain, I thought I wanted to do mathematics, but in the final year at school, I had a fantastic teacher in physics. She was inspiring, and then I decided to do physics. Once I started to do physics, after 3 years of sort of general physics that you studied in Spain, then you had 2 years of a specialization. I decided to do astronomy, a little bit by chance, really. I think that I would have equally liked doing research in any other topic. Then once I got there, I was given the opportunity of doing a PhD in Durham by the person who became my supervisor, and his work was at the time on observational astronomy, on how particular type of galaxies work behave in clusters, and I started then, and that sort of triggered my interest in the environmental effect on galaxy evolution. And I moved a little bit from just looking at clusters to look at much larger scale in the universe, the whole cosmic web full of clusters, filament sheets, voids, and see how galaxies in all these environments are different, and trying to understand the physical mechanisms that make them like that. So it's kind of a little bit evolving from what I started doing at that time, and then developing with the technology and developing with the size of the surveys and the data that was available.
So going back to when you talked about the massive cosmic structure, filaments, the massive cosmic web,
Yeah.
How do we actually sort of study these things? It seems like such a huge thing compared to, you know, the size of Earth and the seemingly small resolution of our satellites that we'd be able to sort of study these. So how would we be able to actually take data and...
So our knowledge of the cosmic web, which is, as it says, it looks really like a web. You look at pictures of it and you can see that it's got sort of the knots, the nodes are clusters and groups of galaxies linked by filaments, sometimes by sheets. So partially we know about that theoretically by building models inside computers that allow to track how matter clusters and distributes itself in the universe, dominated pretty much by gravity and by the effect of dark matter. And so that generates that sort of structure. And then observationally, the thing that gives us the information is what is normally called surveys of galaxies, particularly redshift surveys. So there have been a series of very influential large surveys that what they do is they take a very large patch of the sky, maybe a third of the sky, and take images of those all the galaxies, and then measure the what is called the redshifts that allow us to get the distance to these galaxies. And if you get the position and the distance, then you can build a three-dimensional map. There are two particularly influential surveys. One is called the 2-degree field survey that was built and carried out in the Anglo-Australian telescope. It was the Anglo-Australian telescope at the time. The angular part has dropped of that telescope. And some people that worked in Nottingham were instrumental in that survey, like Steve Maddox. And then the other one is this, they call Sloan Digital Sky Survey, that has really imaged and done redshifts over 1/3 of the sky, order of 1 million redshifts. So you can imagine that if you know the position on the sky of all the galaxies, you can build them up and follow where they are. And that is how it is done.
All right, okay. That's quite inspiring. So what you're saying is we basically just kind of do a sky survey of every single galaxy we could possibly see.
Yes.
Wow, and then how do you actually quantify the properties of these galaxies after you've sort of seen them?
Good. So that's a very good question. So two things. Both the images and the spectra not only tell us where the galaxies are, so that we can put them on the map, but also give us information on the properties, information on whether they're forming stars or not, whether they've got an active galactic nucleus, that is an active black hole at the center that is being fed. It tells us how many stars they have, how massive they are, how old their stellar populations are. We get all that information from the spectrum of the galaxy. That is the spectrum, which is basically the distribution of light at different wavelengths and different colors. And that information tells us about what stellar populations they contain, how many stars they are forming, whether they're forming stars or not, what chemical composition they have. And we can do that not just for the whole galaxy. We can also map inside the galaxy, do a resolved map of the galaxies. And that is something that we work quite a lot here in Nottingham. Part of the Sloan Digital Sky Survey using a technique that has got the fancy name of integral field spectroscopy. But what it actually does is takes a galaxy and makes a map of its light, takes spectra in each position of the galaxy. And so we can learn not only the global properties of the galaxies, but the local properties of the galaxies. Is the center of the galaxy forming more stars than the periphery? Is the periphery older or younger? Is the chemical composition the same? And we've done quite a lot of work here in Nottingham. And then you can link the properties of those galaxies to where they are in that map and think, well, in the environment of this galaxy, which happens to be in a filament or happens to be in a group, is it forming more stars than this other galaxy? Is the morphology, the images tell me what kind of galaxies there are, whether they are spiral or elliptical or irregular. Different galaxies have got different shapes, and we get that from the images. But then the spectroscopy gives us the details on what they are made of.
Right. So the spectroscopy is essentially taking light from this galaxy and just sort of analyzing every single wavelength or frequency.
Exactly.
Light.
You just spread all the light, and then you analyze every wavelength, and that information that encodes an awful lot of information on the stars that it contains, how those stars are moving, what amount of gas they have, lots of the properties of the galaxy.
Seems like an incredible amount of information contained in just sort of some amount of light, which is almost sort of the only piece of information we could possibly get as well.
From galaxies, yes, we cannot travel there, we cannot get material from them. We can look at our own galaxy, the Milky Way, and have much more detail, because in that case we can see individual stars.
Yeah.
In a few galaxies near the Milky Way, we can also see individual stars and then learn from them. But the only material we can analyze on Earth comes from our own solar system, right?
Yeah.
Exclusively from almost exclusively from Earth and meteorites and the Moon, and sometimes comets.
So, talking about the Milky Way, it's true that we are actually observing these other galaxies from within the Milky Way.
Right.
So how do other stars sort of being in the way affect our view of the other more distant galaxies?
Right. So stars do not affect much what we can actually observe. Stars, for all intents and purposes, are just point sources. Okay, because they are so far away. If a star is very bright, you cannot observe a galaxy near it because it sort of outshines the galaxy. But in general, that is not a big problem. The biggest problem that the Milky Way does in terms of allowing us observing other galaxies is not coming from the stars, it's coming from the dust. So the Milky Way, particularly close to the plane of the Milky Way is a disk galaxy that is rotating. It's got spiral arms and it's got maybe 100 billion stars. But also it has dust in the plane. And because the sun is in the plane of the galaxy, if you're looking through the plane of the galaxy, you encounter lots of that dust that is very opaque to much of the light. Certainly opaque to most of the visible light, although it's a little bit more transparent in the infrared. So what we do when we study the extragalactic universe, that is other galaxies outside our own galaxy, is we look away from that plane.
Right.
Okay. And if you look, that plane is quite thin, so the amount of dust we need to see through, which is quite opaque for any wavelengths, is small, and then we can see those other galaxies. I mean, when astronomers call dust something that is probably can be described better as soot, very thin particles made out of sometimes organic materials like carbon, silicon, things like that.
Okay. Going back to how you talked about looking outside of this plane, that does remind me that not only is our solar system sort of planar, but isn't it true that a lot of galaxies are also quite flat?
Yes. Yeah. So what we call spiral galaxies, which in many ways is the majority, have got a very thin or reasonably thin flat disk in which stars are rotating, and that is where the dust and most of the gas is. Okay. The galaxies also tend to have a little bit of a spheroidal round component at the center that sometimes is quite small. In the Milky Way, it's very small, comparatively speaking. And there are other galaxies that are more spherical, more spheroidal, round, maybe elliptical. Those are probably in smaller numbers. They're larger. The more massive galaxies tend to be more rounder, more elliptical than the less massive galaxies. But in general, most galaxies are quite flat disks of stars and dust and gas.
Why do we think that is currently?
Oh, that's because they are rotating.
Right.
If you've got a system of matter that is rotating, okay, the laws of physics, conservation of angular momentum, and the way gas interacts makes most of the material settle onto a plane. Okay, and that plane is rotating so that requires rotation, that requires ordered motions. In some stars in which the rotation is less significant, the stars are more randomly orbiting the galaxy, and therefore they're more spheroidal, more elliptical, rather than flat. So it's got to do with how fast and how important rotation, or what we call physically rotational support, is for those galaxies. But most galaxies have got a significant amount or large amount of rotational support, and they're therefore flat.
What's one of the most sort of exciting finds or findings in your field at the moment?
I think, okay, first of all, is being able to map very large volumes of space and have samples that are very large, that allow us to look at sometimes small, subtle, but important effects. I think we don't really know yet how important sort of more tenuous structures like filaments and walls affect galaxy evolution. We know that clusters affect them quite a lot, but there seems to be some of that effect in those scales when we're talking about filaments and walls.
Right.
But that's still quite controversial. We're doing quite a lot of work on that. But in the field of extragalactic astronomy, I would say that at the moment, one of the things that is most exciting is finding galaxies that were fully formed and quite massive very early on. And it's not very clear how that happened. That has been discovered with the James Webb telescope.
Yeah.
Okay, so finding galaxies when the universe was perhaps only a few 100 million years, a couple of 100 million years, which doesn't sound very early, but it's quite early. If the universe is about 13, 14 billion years old, it's just, well, galaxies forming when the universe was significantly less than 10% of its present age. People thought, and they still are having difficulty understanding how that can happen so early. So that's something very interesting. In other areas of astronomy, I find it fascinating, the detection of gravitational waves, the imaging of the horizon to black holes. I think that is absolutely fascinating. We've sort of known for quite some time that every single galaxy, or most galaxies, have got a supermassive black hole at the center. Yeah. Some of them are being fed, and then they eject a lot of energy in the form of active galactic nuclei. Some of them are not, like our own Milky Way is quite quiescent. There is a black hole at the center, but it's not being fed much. But the fact that we can actually image that black hole, or at least the shadow of the what is called the event horizon, which tells us that there is a real black hole. There's no doubt that that is a black hole. I think that is very exciting.
That is actually extremely it's extremely interesting. Because black holes have been theorized for about 100 years, from going back to Einstein's theory of general relativity, and the fact that it's been a theoretical object or artifact for that many decades, and yet people place so much trust and faith in the idea as if it's confirmed to be correct, when it never really was confirmed. But the fact that we now have an image of that, it's extremely inspiring.
I think people had more than faith. People had science behind it. So there was the fact that we could see in X-rays objects that Cygnus X1, that is a binary system in which a star is orbiting something that is too massive to be anything else but a black hole. Was physics telling us that happened there. Then looking at our own Milky Way, we saw stars orbiting something very small, very massive, and from how those stars were moving very fast around that, only a black hole could be there. Of course, it is absolutely fantastic to be able to image it and say it is there. It's also fantastic to have been able to detect mergers of black holes in gravitational waves. The final stages of these black holes spiraling into each other, merging, and those gravitational waves that come from those last instants of the life of those massive black holes is fantastic.
So how does the behavior of black holes actually play into your current field? I know that you study a lot of black holes that are at the center of galaxies.
Yes.
So what kind of properties do they exhibit that are different to the typical black holes we may see inside galaxies but not at the center?
Right. So we can divide black holes in several categories. I mean, there could be some primordial ones that appeared in the Big Bang, but there's no strong evidence. But we know that there are black holes of masses of stars, stellar masses, which are the end product of the life of massive stars. That's more massive than maybe 10, 20 solar masses may leave a black hole behind.
Mm-hmm.
And those are, they've been detected in binaries, but there's also at the other extreme, so those could be maybe a few solar masses, maybe 10 solar masses. Then you got more massive black holes, supermassive black holes at the center of galaxies. Like each galaxy seems to have one at the center, mostly one. Some of them may have two that are in the process of merging. So the ones that affect my own research more directly are the ones at the center of galaxies, because those black holes power active galactic nuclei. Whenever you feed them with gas, that gas falls onto the black hole and releases a lot of energy. And that energy affects the evolution of galaxies. So we think that through a process that we call feedback, black holes, active galactic nuclei, may prevent galaxies from forming stars. If not, many more stars would form, at least in more massive galaxies. Okay, so that is important. So that's why one of the questions that we ask is, are the effects of these active galactic nuclei dependent on the environment? Are they more important? Do they exist more in clusters or outside clusters? That can be affected by the environment, because to make a black hole have an effect on the galaxy, you need to feed it. And whether you're feeding it with gas or whether you're removing the gas from the galaxy may depend on where that galaxy is. So that's how it affects the kind of research that we do on galaxies and the environment.
Okay. And how does sort of the mass of the particular galaxy you're looking at play into this? So do larger galaxies tend to have a lot larger black holes? Is it the other way around?
No, it is exactly that. I mean, there is a very good correlation between the mass of the galaxy, in particular, the mass of the central region, the spheroidal region of the galaxy, and the black hole at the center of the galaxy. There is a good correlation. I mean, there's a scatter that, it's not a one-to-one relation, but that is telling us that those supermassive black holes and the galaxies that they inhabit co-evolve together, and one has an effect on the other. The growth of the galaxy probably is linked to the growth of the black hole, and the black hole itself affects the growth of the galaxy through that process of feedback, that the black hole can inject energy into the galaxy, preventing new stars from forming. So that they are very clearly connected, and yes, there is a correlation. The most massive galaxies tend to have the most massive black holes, but they're not all active at the same time. A galaxy may have the black hole at the center, and we know it is there because stars move around it very fast, but they may not be fed, and therefore they do not output the amount of energy an active galactic nucleus can.
Could that be sort of reduced down to a distance issue? For example, the stars are too distant from the black hole to be fed into it, or is it like...
You mostly feed gas rather than stars.
Sorry, gas.
Gas. So it is more on whether the gas has been removed, and of course it needs to be close enough. It needs to be moving close enough to the black hole so that it can feed it. And the same black hole in one galaxy sometimes may be fed, and sometimes it may not. Just depends on what's happening with the gas. Gas may be removed by interaction with other galaxies, by interactions with the intracluster medium, that is the gas inside the clusters, and so that may or may not affect how gas is fed into the black hole, how much gas there is to be fed into the black hole.
You made an interesting point earlier. You just briefly mentioned the fact that some galaxies have black holes, but more than one, and they orbit each other. What would happen if those two black holes were to sort of merge and collide? What would happen to the rest of the galaxy surrounding it?
Not much.
Not much?
No. So the actual region that a black hole on its own that is not being fed affects is quite small. So when two black holes orbit each other, they lose energy through gravitational waves, and eventually they may end up merging, because if they lose energy, they gravity wins, right? They keep pulling them closer and closer together, and they will end up merged. And so they will emit gravitational waves, but the galaxy will not notice much.
That's surprising to me, because I thought that because these black holes are so supermassive, that surely it would have an effect, no?
Well, but they are only maybe 1,000th of the mass of the galaxy. Right? They may be 10 to the 6 solar masses, but a galaxy, so that's 1 million solar masses.
Yeah.
But a galaxy may be 10 to the 11 solar masses, which is 100 billion. So it's 100 million times larger. Right. And the sphere of influence of a black hole is tiny. Is only much smaller than the radius of the galaxy.
Right.
And therefore, if the black hole is not being fed, then its gravitational effect only affects a very small region at the center of the galaxy. Now, if the black hole is being fed with gas, then all the gravitational energy or the mass of that gas can be transformed into the energy, or a significant fraction of that mass can be transformed into energy. That is an awful lot of energy, and that can affect the rest of the galaxy.
Yeah.
But a kind of a black hole on its own only affects a very small region at the center of the galaxy.
Right, okay. That's quite surprising to me, actually. I was always under the impression that black holes were a lot bigger than 1,000th of the size of the galaxy.
No, 1 millionth.
1 million, sorry.
Yeah.
Wow.
Yeah.
I think maybe I've been watching too many videos online where they exaggerate the size of it.
So that's the mass. So let me just make sure that I've got the numbers right. So 1 million compare with a 100 billion. So it's maybe 100,000 times larger. Okay. So much more massive.
Right. Okay. Very interesting. Going back to local versus distant galaxies, what's the biggest sort of difference in the properties you see between them?
The local and more distant galaxies.
Yeah.
Right. So if we go back in time, in the last 10 million years, so what we see mostly is that if we just start traveling back in time, that galaxies become more and more active forming stars. So about 10 billion years ago, at what some people call cosmic noon, stars were very actively forming. Galaxies were very active forming stars by probably an order of magnitude, a factor of 10 times faster than today. Okay, so the galaxies about 10 billion years ago had much hotter stars, had more massive stars. They were forming new stars, so they were brighter for their own mass. We'll say. They were also less rich in heavy elements. The chemical composition was not as evolved as today. Remember that the chemical compositions are forming stars. Okay, so if you look back in time, fewer generations of stars had been alive, and therefore the chemical composition was poorer in what we call heavier elements. That is, elements heavier than hydrogen and helium, which are formed mostly in stars or in supernova, but supernova results of stars anyway. So that is up to about 10 billion years ago. And then before that, the information is more sparse because we've got fewer galaxies, but what we see is probably the star formation declined a little bit. So galaxies must have had quite an active period of star formation to start with. It increased, it reached a maximum around 10 billion years ago, 10 billion years ago, and then it declined until today. And today, galaxies, nearby galaxies, which in astronomy, nearby in space means also nearby in time, because light needs to travel to you from the galaxy. In present-day galaxies, in nearby galaxies, the statistical star formation, that is, the average star formation of these galaxies, is significantly smaller than it was in the past.
Right. Okay. Thinking back to how distant galaxies have behaved in the past, does that give you any inclination as to how galaxies will behave in the future?
I think that it is reasonable to expect that the star formation activity in galaxies will continue to decline. For several reasons. One is because the amount of raw material, that is gas and dust, will continue to be used up. Galaxies will, on average, become more and more distant because the universe is becoming larger, because it is expanding, and therefore the possibility of feeding new gas into galaxies will statistically decline as well. There will always be galaxies that for any reason get close to another galaxy, they may merge and they get a burst of star formation. But statistically, my guess is that in the future, the star formation activity will decline and galaxies will become older and the stellar population also older and sort of redder and cooler. Yeah, I think that's probably reasonably safe to say.
Right. So it's a little bit upsetting thinking the galaxy is going to stop forming at some point.
Yes, but at least in this universe, that's probably what's going to happen. Nothing lasts forever, but that's going to happen well after humankind is around in one form or another.
Well, that depends how we actually spend our time here on Earth, isn't it?
Even then, I don't think we're going to last. I don't know, but I suspect, we will be superseded by something else probably.
What else do you think would be superseded by?
Oh, why are we going to be the last thing in evolution in the universe?
Yeah.
The evolution will never stop, either here on Earth or somewhere else.
Yeah.
And complexity of life in one form or another will continue to grow. That's my gut feeling.
That's what you believe. You believe that life is not a chance event, in the sense of it can form multiple times in the universe.
I'm almost certain that that's the case.
Yeah.
I think that's the case. I don't like the word believe.
Yeah.
I try to like the word think much more. I don't think believe is a scientific word. Okay. I like to think that is the case.
Yeah.
That is, I don't know what the probability is, but how frequent life develops in other places. But I think it's hard to think that it is a unique event on Earth.
Yeah.
And one of the things that I do think will happen is when life starts, it's very difficult to stop. Okay. Now, whether intelligent life will continue, I don't know, but we may evolve into forms that do not require a physical form, certainly not a physical form based on carbon.
Yeah.
Carbon is far too fragile.
Silicon?
I don't know, maybe even more sophisticated than that.
Yeah. So do you think there are other life forms elsewhere in the universe at this current point in time?
I suspect there are, yeah.
So
how many, I don't know, because I don't know how easy it is. I would be very surprised if there weren't any in the hundreds of billions of galaxies with hundreds of billions of stars.
Yeah. So you take more of an optimistic viewpoint of that? Because I know there are a lot of scientists that do take the opposite viewpoint, where they say, no, the chances of life on Earth happening are so minuscule, so infinitesimally small, that it's almost impossible to conceive of that happening somewhere else.
Now we're maybe talking about life or intelligent life. I think life, as in self-replicating matter, I don't think that's can be possible. I think that the universe is far too vast for that not happening in many other places. We see complex organic matter in many places in the universe, and we've explored so little. In terms of intelligent life, I don't know. I would be surprised. Yeah. But I mean, the safe thing to say is that I don't know, because we haven't communicated with anybody else. Maybe the distances are so vast. Maybe the chances are that it only happens once per galaxy, and therefore the distances are too vast and the energy requirements to communicate too vast to know for sure. I don't know, but I mean, I know that we are here. I know that they are reasonably intelligent, or at least complex enough, and probably some form of conscious beings will survive one way or another. They may not survive on this Earth, or they may not survive in this, well, certainly not in this current form. We have got to evolve, right? We cannot just stay as this, just evolution happens. I think that that's what's going to happen. At some point, I just stopped worrying about it, right? I'll retire soon, and I will be dead, in not too distant future, and that doesn't worry me too much. I take a very pragmatic view to all of this.
Mm-hmm. Right. Okay. That is extremely interesting. Yeah, because a lot of scientists do take the viewpoint that they take into account the Fermi paradox. If you've heard of that.
Yeah.
Do you mind explaining that to our viewers, what the Fermi paradox actually is?
So what that paradox says is that if life is reasonably probable to happen, some other civilization would have started earlier than us, and they would be more advanced, and they would have communicated with us by now. That depends very much on how frequent that is. If it only happens in 1 in 10 galaxies, right, the distance to the nearest 10th galaxy is so large, and the amount of energy required to communicate is too large to have happened. But I don't know whether that happens 1 in every galaxy, 1 in every 10 galaxies, 1 in every 1,000 galaxies, 1 in every million galaxies, 1 in every billion galaxies. We've got 100 of those, right?
Yes.
So I don't think the Fermi paradox is strong enough to be applied to the whole and the vastness of the universe.
Yeah.
So there may be other lives. And the other thing, of course, is we don't know how long intelligence life in a particular event lasts.
Yeah.
Whether they are able to survive in another form that doesn't depend on the resources of a single planet or a single star or even a single galaxy.
Wow. And do you think?
But I don't know.
You don't know.
I don't know. Let's just put that always as the caveat. I can't speculate.
Yeah, that's your get out of jail free card.
Yeah.
So how would you say, obviously with recent advancements in technology, with James Webb, with other telescopes are on the horizon now, how has that impacted your field in particular, interpreting data from galaxies?
Oh, enormously. When I started doing my PhD, Hubble Space Telescope was not out there.
Yeah.
For the largest telescopes at the time were 4 meters. I did my thesis using a 4-meter telescope, 3.8-meter telescope in Hawaii.
Yeah.
The United Kingdom infrared telescope, that was the basic telescope that I used. And then 8 and 10-meter telescopes came, the VLT and the European Space Observatory, Keck on Hawaii. Now there are several others, Gemini, Subaru. Now the next generation of telescopes will be 30, 40 meters in diameter. You've got to remember that the light gathering capacity of the telescope goes with the square of its radius. So if a telescope goes from 10 meters to 20 meters, it can gather 4 times more, so it's a factor of 2 in diameter, so it's a factor of 4 in area. It can see things that are 4 times fainter, so that gets you farther away in distance. So we're gonna go from 8 10-meter telescopes to a 40-meter telescopes. That's a factor of 4, so 16 times more light gathering abilities. And then there is all the space telescopes. What significant space telescopes we've had? Well, Hubble Space Telescope, right? Suddenly we were able to, the galaxies that when I was doing my thesis were just a blob on an image. We could see in detail, we could see the spiral arms, we could see that there were spiral galaxies, we could measure whether they were forming stars or not. That was Hubble Space Telescope. Then there have been other telescopes looking at the other wavelengths. We've had X-ray telescopes that have told us about matter in clusters, what are clusters made of. ROSA, XMM, Chandra, to mention the most influential ones. Then, of course, now we've got JWST, James Webb Telescope, which again is much larger diameter. It can see farther back in time, farther away in space. We've had also something very important. In fact, today I've just learned that Gaia, which is a telescope that has mapped our own galaxy in exquisite detail, is measured the positions and distances of many billions of stars, is being switched off. They've run out of the propellant that they require to keep it in position and to keep scanning the sky. So that has given us, and will continue giving us, because nobody has really finished analyzing that data, a map of our own galaxy. So our own galaxy, we need to learn how it is in excruciating detail so that we can apply that to other galaxies. So those is the kind of advancing technology that makes the study of galaxies progress. All of those things, and I'm sure I'm measuring and forgetting many other advances. Okay, larger telescopes on Earth and orbiting and cleverer telescopes out around the Earth.
Have you ever been to one of the observatories on Earth?
Oh yeah, I spent many nights on Mauna Kea in Hawaii, many nights in La Silla in Chile, and on the observatory in La Palma, on the VLT and in Paranal, Anglo-Australian telescopes, many telescopes, yes. Nowadays, there is less traveling to telescopes than there was when I was younger. I've spent many nights on mountains using telescopes, yes. That was fun. Hard sometimes. Mauna Kea is a very uncomfortable place to work, because it's very high, and then you get altitude sickness and very dry. But that is what makes it uniquely good.
Yeah, it's one of my dreams to actually go visit one of these observatories and see the nice views. So what was that experience actually like for you?
Okay, initially it was very spectacular, and then at some point it became part of the job, right?
Yeah.
It was really nice. It was really being outside on the mountain looking at the sky. The time was fantastic. I'm now partially blind, so my eyesight has suffered enormously in the last 20 years. So I cannot really see very well at night, and so my ability to appreciate the night skies has gone down. But at the time, I could just go out and with my own eyes. That was the most impressive thing. Because when you're actually working at the telescope, you're in a computer room, right? Yeah. You're inside the computer room, surrounded by screens, issuing commands to the telescope, or looking at the data that is being taken, or just waiting until the 3-hour exposure that you've started finishes. So, but it is spectacularly and spectacularly beautiful.
What was your favorite one to visit?
Perhaps scientifically not the most powerful, but I like Tololo, Cerro Tololo in Chile. I think it's a beautiful, very beautiful location. Yeah, in many ways that is my favorite. I've done better science with other telescopes, but Tololo is a very beautiful, architecturally very beautiful as well, with the telescopes there. The observatory is a very pleasant place.
Wow, okay. It's got a special place in your heart.
A little bit. Whenever I'm on top of that mountain, sometimes it reminds me of the Campidoglio in Rome, that hill. For some unknown reason, it's got telescopes at the corners, and it's got a plateau, and it's got lines, white lines that join them, which if you've ever been to Rome and you go to the Capitoline Hill, the Campidoglio there, it reminds me of that. I like architecture very much.
Right, okay. If you could visit any galaxy that you learned about, throughout your whole career, which one would you visit and why?
The problem is visiting a galaxy. Just go and get inside the galaxy, and you just a little bit small to look at it. I think that rather than visiting another galaxy, I would like to visit another solar system that is another star in our own galaxy, because there's plenty of stars in our own galaxies with complex solar systems with many planets. I think that would be, given the scale of a human being, that is something easier to comprehend than going to another galaxy. Yeah. Once you're inside the galaxy, you just see stars around you.
Let me change the question then. So which star would you visit in that galaxy?
Any with a complex, the problem is that those stars that have got complex planetary systems around have got no names, they've got just numbers, and I can't remember those numbers. But there is some of them have got multiple planets, some of them, and I would like to visit any of those.
Yeah. I've heard that, on average, every star has multiple planets. Is that correct?
I think that's probably correct. Yeah. Pretty much everywhere that we've looked, they have.
Yeah. And so, what do you think with regards to the previous topic we were talking about? there are probably billions of stars in our galaxy,
Yes.
so multiple billions of planets. What percentage of those do you think would be habitable for life?
Habitable for life?
Yeah.
That I don't know, and then people are trying to find out what is the fraction of planets in the habitable zone. And the main problem is that our own solar system doesn't seem to be very similar to the solar systems we found outside, mostly because of observational limitations. We are able to detect mostly very massive planets that are very close to the stars. When we look at the solar system, the most massive planets are quite far away from the star. Okay, so we don't know really the statistic of the planets around the stars in an unbiased way, a way that is not determined by what we can actually see. We only see what we can see at the moment. We cannot just see every single planetary system, and therefore we don't know how likely it is that planets are in the habitable zone, which we normally define as the zone where water can exist in liquid form, because the kind of life that we understand has got a chemistry that requires things to be dissolved in water.
So there must be loads of different theoretical models, right, that you must be sort of studying in terms of galaxy formation and things. What are the two sort of, or not the two, but what are the main competing models that you are kind of analyzing data, I guess?
So, interestingly, things have converged very much in the last maybe 20 years into what we sort of think this is the standard cosmological model. The determining factors in a cosmological model is what is the universe made of, what fraction of its matter is dark, what fraction of its matter is normal matter, like atoms and molecules and protons and electrons, and what is the effect of what we call dark energy. Okay, let me rephrase all of that. The universe is expanding, and is expanding faster with time, which is very difficult to understand. We never thought that when I was young, and we thought that the universe was slowing down because gravity would slow down, but that increase in the expansion rate is caused by something we got no idea what it is. We call it dark energy. So how much of that we have and what properties it has determines much of how the universe evolves. Also, when we go to matter, most of the universe is made out of what is called dark matter. That is matter that doesn't shine. And we know it's there because it attracts other matter through gravity. And only a small fraction, maybe 5%, is normal matter. Excuse me. So if that is the model we start with, and we think that dark matter is what we call cold dark matter, that is, it doesn't move very fast, then the models have converged into what we call the lambda cold dark matter cosmology, in which you got maybe 70% is dark energy, 20-something% is dark matter, and the rest is just a normal matter. And if you put that in your computer, then most theoretical models give results that are similar. The main differences come when you go into the details of the messy physics, the physics of gas, the physics of baryons, the physics of normal matter, and how much star formation there is, how much star formation is suppressed, and all those details we still don't know what the effect of galactic nuclei are on galaxies. So those are the things that you're testing. You're testing how important is that switching off of star formation by active galactic nuclei. How do you model in your computers the things that you cannot resolve inside your computer? Your computer doesn't have enough power to have a model with every single atom, right? The smallest unit that you can have there may be 10 to the 6 times the mass of the sun. Okay, so that's, you don't even go star by star when you do those models. So the physics that is used there is what is uncertain. Now, you can go outside that sort of standard, most commonly accepted model, which is what we call lambda core dark matter. That's just the label of the model that I described. But you can say that dark matter is of a different nature, or dark energy behaves in a different way, and that will have global consequences that are larger. But in general, there's very little evidence that we need to throw away completely this lambda core dark matter model. There may be things that it doesn't explain perfectly, but for the time being, I see no reason to throw it away, and I will be testing what I observe against the details of galaxy evolution rather than the details of the cosmological model.
Yeah. So do you think in the future this will be able to solve some of the problems that we currently can't solve at the moment?
Well, we have got the two kind of parallel, strongly interacting ways we learn about the universe. We learn about the universe by observing it, by having larger surveys, mapping it better, more galaxies, larger statistics, more details of every galaxy, going farther away in time, earlier in the universe by going farther and farther away, fainter and fainter galaxies. And that observational side talks to models, computational models of how the universe evolves and how the galaxies that live in it evolve, in which the resolution keeps getting larger. What I mean is that you can look at smaller and smaller details and put in more detailed physics, because the computing power keeps growing. And both methods need to talk to each other, right?
Yeah.
Observations find things that the models have not predicted. The models predict properties of the universe that are not observed. And in that dialogue, saying, look, the galaxies that you're predicting are forming too many stars, so therefore you need to put something new in your models, maybe stronger effect of those active nuclei that we talked about at the beginning to suppress star formation. Maybe your models are not considering strong enough environmental effects when we observe them, or vice versa. That dialogue makes progress.
So what do you think is the biggest unanswered question in your field today?
I think the nature of dark matter and dark energy. Those are labels of our ignorance. Yeah. Right? It's just the universe is expanding faster and faster. There must be something that does it. We call that dark energy, but we've got no idea what it is.
Yeah.
Dark matter, we seem to be finding things have got more mass than they should have, from the way they move, from the way their components move. That means that there must be some missing mass. We don't see it, it doesn't shine, it doesn't emit radiation of any kind, but we see its gravitational effects. We call that dark matter. Either that, or our understanding of gravity is wrong.
Yeah.
Okay? So those I really would like to know, and I hope maybe we will learn before I die what dark matter is and what is the nature of this thing that we call dark energy. I think those are the fundamental things. I mean, the details on how galaxies evolve, on what happens to a black hole are fascinating and very interesting physics in there, but they're not, I think, as fundamental as the essential components of the universe that appear to be there, and quite frankly, we just have got labels to them, dark matter and dark energy, but we don't know what they are at all.
Do most galaxies have dark matter halos around them? Or?
The vast majority have, yes.
And do we know how they sort of behave, or are we just observe them?
Well, we can observe how large they are, because we see how far the gravitational effect is. We have some idea of what the density profile is, whether, how much matter there is per unit volume at different distance from the center. All those things we can measure a little bit, and we can model them as well in the computer. We can compare the predictions of those models from the observations.
So what are the kind of main ideas as to what dark matter could be at the moment?
Well, they could be reasonably massive fundamental particles. Okay, so that's why they're massive, and therefore they move slowly, and that's why we call them cold. There are some interesting ideas nowadays that they could be actually extremely light. sort of much lighter than any particles we've seen, and that they would be so light that, let me get technical for a second, that the wavelength of those, the Berkeley wavelength of those particles will be comparable to cosmical structures, and they call that sometimes wave dark matter or fuzzy dark matter, but still we don't know what they are.
Mm-hmm.
Okay, so yeah.
And then with regards to dark energy, which is a completely different phenomenon, do we have any idea as to what that could be as well?
Not really.
No.
Not really. It's just there's even the amount that there is doesn't seem to fit anywhere.
Okay. I think we've covered quite a lot of ground today.
Yeah.
My final question for you today would be, how has studying extragalactic astronomy and observational cosmology shaped your personal perspective on humanity's place in the cosmos?
I think I always find that the fact that we are here asking those questions is the interesting thing.
Yeah.
Right. The universe would be a lot less interesting if nobody was looking at it from inside and asking, what am I made of, or what is the universe going to do, or what has it done in the past. It makes it more interesting. So consciousness for me is fundamental to the universe itself.
Right.
I'm not completely sure whether a universe in which there's no consciousness, at least at some point, makes any sense in my head.
Mm.
So that's consciousness, humankind or whatever, I don't mind. It's anything that is conscious that can look out and ask these questions, or maybe even give some answers that may be correct.
Wow, that's quite eye-opening. Yeah. Well, anyways, I think we've had a fantastic interview.
Right.
We've had an amazing conversation. I think we're going to end it here today.
Okay.
I'd like to thank you very much again for your time, and I look forward to having more conversations with you in the future. And
very relevantly, there are 2 students out of that door who are going to have a meeting with me on a project that they're doing on looking at the effect of the environment on the star formation distribution of galaxies with data that my group took.
Okay.
So
awesome.
that is what I'm doing now, and they're just waiting there, and in fact I think they are impatient because
are they messaging you?
they're 2 minutes into the time, so
okay.
I've got to stop here.
All right, no problem. Sorry for taking up your time.
No, that's fine.